convergence. So this is where we start looking at, okay, when we have a sequence versus when we have a series. So we'll be referencing both. So there'll be times I'll even misspeak. But in general, when we are taking a look at a series, it is when we sum up the list of numbers from our sequence. Okay, so a sequence is a list of numbers, right? So when we have a sequence, that is when we just have a list of numbers. So like whatever, 1, 3, 5, and so on. And then as soon as we sum up those values, then we have a series. And so when we look at this right here, this is a capital Greek letter sigma, right? And so when we write n is equal from 1 to infinity, we're saying we're starting with a first term, and then a second term, third term, fourth term, all the way to infinitely many terms, right? So that is what we have. And so we have a sub n, so that would be our rule. And then if we want to generate the values of that series, then we would substitute in whatever that starting number is into whatever that rule is. And that's how we find that. And then we sum up those values, and then that gives us our infinite series. But that's all we're going to work with is infinite series. So we're just going to use series. I'm not going to say infinite anytime. Okay, so our numbers are called the terms of the series. So this would be our first term. This would be our second term, our third term, and so on. And then as a shortcut way to write out an infinite series, this is an accepted notation. So even though we won't have the index on here, like n equals 1 to infinity, this is what we will use to say infinite series. Or if you don't like that notation, just write out the words infinite series. Okay, so what does it mean for a series to diverge or converge? Okay, so what does it mean for a series to diverge or to converge? So if we have an infinite series, we have to first define what we call the nth partial sum. So the nth partial sum. So that definition is this part right here. Okay, so Sn is equal to A1 plus A2, so on and so forth. So what does that even mean? So remember that it's an infinite series. So if I ask you to like add up all the numbers of the infinite series, like you're going to be there for a while. But if I ask you to find me the third partial sum, then we're all going to do a little happy dance, because what does that mean? So the third partial sum, so that notation would be S with a subscript of 3, means, well, just add up the first 3 terms. So that's what that means, right? So if I say the nth partial sum, you're just adding up however many terms I ask you to. So if I ask you to add them all up, there might be a little bit of tears, because when's that going to happen? All right, so that's the nth partial sum. So now the second component is we have to look at, well, what the heck is a sequence of partial sums? What is a sequence of partial sums? Well, a sequence means a list of sums, right? So a list of sums. So if I want a sequence of partial sums, that would be something like the first partial sum, and then the second partial sum, then the third partial sum, and so on. That would be a sequence, meaning a list of the partial sums. So what is the first term added to nothing? What is the first 2 terms, right? S2 would be the first 2 terms added. What are the first 3 terms added, and so forth. So if that sequence of partial sums converges to a particular value, so if the sequence converges, then we can say the series converges. So if the sequence converges, sequence of partial sums converge, then our series does as well. And then that value, that limit value that we created, whatever that is actually the sum of the series. Okay, and so then if the sequence of partial sums diverges, then our series diverges. So there's like a lot, like that's a lot to think about. All right, so moving on. Okay, so we'll address that. Like that'll make hopefully a little bit more sense here in just a second. Okay, so let's take a look at, so what is our 2 basic questions? So I'm going to actually leave that up there so we can see that. So the 2 basic questions for at least the first half of chapter series, or of chapter 8, is we want to know, does the series actually converge or diverge? That's like our number 1 question for the first at least half of chapter 8. And then if it converges, occasionally, not all that often, we will ask for that sum. Okay, so if that series converges, then we will ask for the sum. Okay, so let's start with question 1. So here it's asking you to find the first 5 terms of the sequence of partial sums. So the first 5 terms of the sequence of partial sums. So remember what the sequence of partial sums is. It's asking for S1, S2, S3, so on and so forth. So if they're asking for the first 5 terms, they're asking you to find S1, S2, S3, S4, S5. So the first 5 terms of the sequence of partial sums, which is not the first 5 terms of the series, right? Totally different. But we can't get started until we actually find the first 5 terms. So what we're going to do over here is I'm going to find the first 5 terms of this. So we're starting at n equals 1, and we can start anywhere. So this is starting at 1, though. They're telling us to start at 1. So I'm going to replace n with 1. So 1, 3 to the power of 1, and then plus, because we're doing a sum, and then 1 over 3 to the power of 2, 1 over 3 to the power of 3, 1 over 3 to the power of 4, and then 1 over 3 to the power of 5, and then I'm going to go dot, 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 because it's infinite, right? So it goes on forever. But there are my first 5 terms of the sequence. So now I want to find the first 5 terms of the sequence of partial sums. So that means I need to find S1. So I want to sum up the first term. So that would be just 1 over 3 to the first, or 1/3. So there's the first term. And so then now I want to find S2. So I'm looking for the second partial sum, which means I'm only going to add up the first 2 terms. So then I'm going to take 1 over 3 to the first, so 1/3, and then I'm going to add that to 1 over 3 squared, which is 1/9. And so that would be 3/9 plus 1/9, which is 4/9, right? So there's S1, there's S2. And so now I need to find S3. So S3 means I'm going to add up the first 3 terms. So the first term is 1/3. The second term is 1/9. The third term is 1 over 3 cubed, which is 1 over 27. And then now I want to add those up. Well, I already know what this adds up to, right? That's from before. So that's 4/9. And then I'm going to add to that 1 over 27. So that would be 12/27 plus 1/27, which is 13 over 27. Okay, so do you see where we're headed there? And so we have, oops, trying to click on that. There we go. Give myself a little space. So then now I'm not done though, right? I got to find the first 5. So then S4 is going to be adding up the first 3 terms, which we already did. So that was S3. Plus the 4th term, so 1 over 3 to the 4th, which is 1 over 81. And then remember, S3 equaled to 13 over 27, right? So from above. And then I want to add that to 1 over 81. So that would be 39 plus 1, so 40 over 81. Almost finished, right? So we need to find S5 also. So that means we're going to take S4, which was 40 over 81, and we're going to add that to the 5th term. So that's this one here. So that would be 1 over 3 to the 5th. Hold on, I'm doing 81 times 3 in my head. So 243. Yeah, there we go. So then that would be 120 plus 1, so 121 over 243. And there we go. So there is my first 5 terms of the sequence of partial sums. Okay, so that's what they were asking us. So now the second component of that definition, so up here, right? So now if we take a look at that sequence of partial sums, we want to know, does that converge or does that diverge? Okay, so that's the second piece. Okay, so let's go ahead and take a look at that component. So that is down at the bottom. Okay, so does the sequence converge or diverge? So I'm going to just list them out here. So my sequence of partial sums that I have is 1/3, 4/9, 13 over 27, 40 over 81, 121 over 243, right? And then so on and so forth. So what I'm looking for is, does the series converge? So if it converges, it's going to settle in on a particular value. If it diverges, it's not. Like maybe it bounces back and forth, like 2, -2, 3, -3, 4, -4, 5, -5, 5, -5, so on and so forth. Or does it look like it's leveling out and approaching a particular value? So if I do decimals here, so that would be like 0.3 repeating, right? 4/9 is, I don't know, what is that? Almost a half, right? Because 4.5 over 9 would be a half, so that's got to be a 0.4 something, right? 13 over 27, also close to a half, right? Like that's, what, let me get a calculator out so that I'm not guessing. Hold on, I'm getting a calculator. Probably should have had that already. Okay, so if I did 13 divided by 27, so that's 0.48, 0.48. And then 40 divided by 81, that decimal also close to a half, right? So 0.49. This one divided also 0.49, but 7. So if I'm looking at this, all of these numbers, right, because half of 27 is 13.5, half of 81 is 40.5, half of 243 is 121.5. And so if I look at all of this here, is that, yeah, it does. It looks like this is leveling out, and it looks like it is converging, right? So because the sequence of partial sums looks like it's converging to 1/2, then my series converges as well. And then it looks like it's converging to about 1/2. So what is happening here, just to kind of make sure we're understanding this, is that I can see that even though I keep adding more value to the next one, right? So when I had S4, so when I added up the first 4 values, I got about 1/2, right? So under a half, but I got about 1/2. And when I added another one, I didn't get bigger than a half. I just got closer to a half. And I'll bet if I found the 6th partial sum, so I added more to this, I don't get bigger than a half. I just get closer to a half. And that's what this is saying. So if I look at this, I know that the sequence, right, the sequence itself is not converging to 1/2, right? The sequence is converging to something else. It's the series, the sum of those numbers, that is converging, and that's converging to about 1/2. Okay? All right, so moving on. So let's take a look at these here. Got a little bigger. Okay, so geometric series. So this is a review off of your Honors Math 2, which was, I don't know, forever ago. So for some of us, it's 2 years ago, and for others, 3 years ago. That was a while ago. So just a reminder, so geometric series was when you had a ratio, right, R, and that was your multiplier. And so when you are, if you had a list of numbers like, I don't know, and so on, something like that, you would say this is geometric because I'm multiplying by 2 each time, right? So my ratio would be equal to 2 because every time I'm just multiplying by 2 to get the next term. So that made it geometric, right? When you had a multiplier, that ratio. And then if it was arithmetic, if you added the same number over and over again. Okay. All right, so what does it mean for a series to converge or diverge? Okay, so this is, again, 2 or 3 years ago, so this is a while ago. So a geometric series is considered divergent if the ratio was greater than or equal to 1, okay? And then if the ratio is somewhere between 0 and 1, then we said the series converges. And then the value of that, right? So the value of that sum, this was a formula that we worked with, that would be A is equal to 1 minus R, and that's provided the index started at 0. which for our like book work and things like that, it will just about always start at 0. But then the AP tests are like, no, we're not going to start at 0, way too easy. And so what we really need to think about is if it doesn't start at 0, we really need to think of the sum of the series to really be what is the value of the first term and then divided by 1 minus r. So if I take a look here, if n were 0, r to the 0 would give me 1, and then a times 1 would just be a, and that's how we're getting that here. But if n were not 0, right, if it were 1, then it would be a times r to the first. And so that's what we really need to think about is when we're learning the formula for a geometric series is not so much memorize this one because that will not be on the AP test. We want to memorize this one because that's what will be on the AP test. So the value of the first term divided by 1 minus r. Okay, so let's take a look at each of these problems here. Okay, so see if we can like maybe jog our memory. So when I look at this right here, so we're determining if this series converges or diverges, and we want to find the sum of the series if it does converge. So the first thing I would look at is I'm like, okay, I'm going to recognize this as geometric. Okay, so I want to make sure I recognize this as geometric. And how am I doing that? Again, I have some sort of coefficient, some sort of ratio to the power of n. So I look to see where is that variable, right? So that variable is in the exponent. That's going to make it geometric. Okay, so that's geometric. So then right here, I recognize that it is geometric. And so what is that ratio? What is that ratio? Okay. Okay, so that ratio is going to be what is to the power, right? What is to the power, or the base of the variable exponent. That's what I want to say. So for this particular problem, I can see that my ratio is negative 2/3. And again, that's because that's the base of that variable exponent. And so because that ratio is negative 2/3, then I can make a conclusion. So that conclusion would be that my infinite series, so that was the notation for that, converges, because I have to justify. And that is, why do I know it converges? Because the absolute value of the ratio is going to be less than 1, right? So that is what it says. So the ratio has to be less than 1 in order for the series to converge, right? So that's what it says right up here, that the ratio has to be somewhere between 0 and 1 in order for the series to converge. And so the absolute value of that is 2/3, and so therefore it will converge. So one thing to kind of think about just to make sure, because the more we have to memorize, the more we're going to mess up, right? So we want to understand a little bit. So if we think about what does it mean for a sum to converge or diverge, is it has to like add up to a particular value, right? So if I look at this geometric series, that first one I wrote out, so here that ratio was 2, right? Because I'm multiplying by 2 each time. So if the ratio is 2, that means I'm like doubling the numbers, right? They're getting bigger and bigger. So if I asked you to add up this infinite list here, you would be like, no can do, because the numbers just keep getting bigger and that sum is going to just sum up to infinity, right? However, if I had my ratio be, say, half, so 2, so if I take half of 2, that would be 1, half of 1 would be a half of that would be a fourth, and so on. And I asked you to add up this number, well, maybe not so pleasant, but what is happening here is every time I keep taking a half, these numbers are going to get smaller and smaller to where eventually we're going to say they approach 0. So at some point, these numbers are going to add up to something, right? It's got to at some point because it's going to hit that 0, where even though I'm at it, towards that infinity mark, whatever that looks like, all of those numbers are going to be add 0, add 0, add 0. So this potentially is what we're looking at in terms of that converging and diverging. All right, so there is that piece. Okay, so here the ratio is negative 2/3. So whenever I multiply by a ratio less than 1, the numbers are getting smaller. And so because every time I add on a smaller number, I'm still not going to add above to infinity. Okay, so what is the formula for finding the sum? So the sum of the series is the value of the first term. So to find that first term, I'm going to replace n with 0. And so negative 2/3 to the 0 is 1, and 1 times 2 is 2. So the value of the first term is 2, and then over 1 minus r, and r was negative 2/3. Okay, so what am I doing? I'm looking right here. So then that would give me 2, and then 1 plus 2/3, so 5/3. And then 2 divided by 5/3 is the same as doing 2 times 3/5. And so that would be 6/5. So that means if I were to list out all of those numbers, it would settle in on that value 6/5. Okay, so moving on, let's take a look at B. So for this one right here, so again, I'm recognizing this is geometric, a couple ways to look at that. I have a variable exponent, right? So there's that variable exponent, and then my ratio is going to be the base of that. So right here, so I can see that my ratio is equal to 1.03. So is that absolute value greater than 1 or less than 1? So because it's bigger than 1, that means my numbers are getting bigger, right? Because I'm multiplying by a number bigger than 1. So if the numbers are getting bigger, it's going to have no chance to converge, because if I keep adding numbers that keep getting bigger and bigger, it's going to add to infinity. And so that means my conclusion is going to be that the infinite series diverges, and that is because the absolute value of the ratio is greater than 1. So the terms are getting larger, so it will not converge. Okay, moving on. Okay, so let's take a look at this one right here. So this one I'm going to do a little rewrite so we can recognize this to be what we need it to be. So this is the same thing as 1/2 to the power of n. So that's what that means, because this would be 1 to the n, which is just 1, and then over 2 to the n, which would be that, right? So those are equal to each other. So whenever we get something that looks a little wonky, make sure you do a little rewrite. Okay, so is this geometric? Yes, this is geometric. How do I know? I have a variable exponent, and then that base is my ratio. So I know that my ratio is equal to 1/2. So if the ratio is 1/2, is that bigger than 1 or less than 1? That is a ratio less than 1. So then that means my series is going to converge. And so why is that? That's because the numbers are going to get smaller and smaller, right? So I'm going to keep adding smaller value that is approaching 0. So my end terms, my tail end terms are approaching 0. So that gives that front stuff a chance to add up to a finite value. And so what would be that sum? So the formula is the value of the first term. So let's find the first term. So I'm going to replace n with 0. 1/2 to the 0 is 1. And then over 1 minus my ratio, which is 1/2. So the sum would just be 2. Okay, last one. So for this one right here, so again, do I know, is this geometric or not? And I do know it's geometric because I have variable exponents, and then they have that common base of 4, right? That common base of 4. So, but I need to simplify it just like I did on the previous one. So I'm going to go ahead and do a little bit of simplifying here. So that 3 I'm just going to have kind of to the front there. So when I'm dividing exponents, so if I have like x to the a over x to the b, I subtract my powers, right? So I would do a minus b. So here I'm going to subtract my exponent. So I have n, and then I want to subtract n minus 1, right? So n minus 1. And then let's go ahead and simplify that. So I'm going to distribute that negative. And then that would be 0, right? So that would be 4 to the first. So 3 times 4. Okay, so this is no longer geometric, right? It started out looking geometric, but now this is asking us for finding out if 3 times 4, right? If that would converge or diverge, right? Like that's what that's asking, okay? So it's no longer geometric. So I can't use the geometric. So I got to use the good old noggin, right? A little intuition here. So this is saying that you're taking 12 and you're going to add that infinitely many times, right? So what's the value of the first term? 12. What's the value of the second term? Still 12. How about the third term? It's still 12. So what do you think? So does this converge or does this diverge? Well, this is going to diverge because if I added 12 repeatedly, it's going to go to infinity. Okay? All right, so let's take a look at one more idea here. So last one. So this one is, well, first just the properties. So this first component here, this is also a review off of Honors Math 2. So this is just giving you, like if you have, what are your basic properties of infinite series, similar to like kind of your limit ideas. So if you have one infinite series that converges and another one converges to whatever those particular values are, so like maybe it converges to a half and 2/3 or something like that, then properties are if I multiply by a coefficient, then the sum would be that same multiple. So if this was, whatever, x, and then the sum was a, then if I did 2x, the sum would be 2a. And then if we have two series that converge, I can add those series together and I would still get a converging series. And likewise, if I subtract the two series, I would get a series that still converges, whose sum would be the difference. Okay? All right, so let's take a look at our last little test. So remember what the goal here is for our chapter 8 is the basic question is, does a series converge? Does it diverge? So everything we're learning here is different tests to determine, given a particular function, like will it converge, will it diverge? So that's just kind of our beginning basis. So this is called the limit of the nth term of a convergent series. If you know that a series converges, the limit of the sequence has to equal 0. So if the series converges, the sequence has to converge to 0, right? So the series converging means it goes to a sum. A sequence converging means it's talking about the tail end terms, right? So this is saying, this part right here, so by saying the sequence is equal to 0, then we are saying the tail end terms, so the ones going out towards infinity, go to 0. So if I have whatever the sum looks like, right? So let's say it's like 1 plus 4 plus, 12 plus so on and so forth. So this right here, the sequence is not going to 0, right? Because they're getting bigger and bigger. So the end terms are not approaching 0. They're approaching something bigger, right? Bigger than 0. And that's just by looking at whatever I have here. However, if I had 1/1, 1/4, 1/12, then when I look at this, like what's happening here, the bigger the denominator, the smaller the number. So I would say that the end terms are approaching 0. Okay, so so sequence versus series, making sure that we're holding on to those thoughts. Okay, so the reverse is not necessarily true. Okay, so here's our nth term test for divergence, which then will address the other piece that I just said. So if the tail end terms of the sequence does not go to 0, then there is no way for there to be a sum, a finite sum. So then we would say the sum of the series, or the series, diverges. So the tail end terms have to go to 0 for there to be a chance for the series to converge. This can be often very confusing for students. So it is really important to understand that if you have a list of numbers, there is no guarantee that if the end terms go to 0, that does not guarantee that this will add up to a finite value. And I'm just going to write A for a finite value. Like that is not a true statement. So wait, actually, let me say that better. So just because the end terms go to 0, it does not mean that the series will converge. It still can diverge. Why is that? Because what could happen is that these guys here can add up to an infinite value before it ever gets to the terms that are 0. So what we would say to that is that if these terms do not drop to 0 quick enough, then it might diverge, meaning add up to infinity. Like that is a possibility. So if these terms here are not dropping fast enough to get to those 0 end terms, then it is possible that these front terms will add to infinity, causing the sum to diverge, even though the end terms go to 0. Okay? So the only thing we can say for certainty is that if the end terms are not 0, then the series diverges. If the end terms are 0, who knows? Maybe converges, maybe diverges. Okay? All right, so let's do these couple of examples here to make sure we can get that point across. Okay, so the first thing we want to know is, does the series converge or diverge? Just like everything, that's going to be always our question, right? So is this geometric? And I would say this is definitely not geometric because the variable is not in the exponent, right? It's not 2 to the n, but n squared. So this is not geometric. So if it's not geometric, the only other test I know is this one right here, right? So what am I going to do? I'm going to take the limit of the sequence. So that means I'm going to drop that little sigma notation, and I'm going to take this limit to infinity. So these are equal power. So because they're equal power growing at same rate, right? So these are growing at the same rate. That limit would be equal to 1 over 1. So which is 1. So is that 0? That is not 0. So then therefore, if I tried to add up those terms, right? Look at that infinite series, it would not add up to anything. It would diverge. Okay, so what is this saying? So just to make sure we're understanding this. So there's going to be a bunch of numbers, right? A bunch of numbers, whatever they are, dot, 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 and what's going to happen at the end? They're all going to be 1. How come? Because this piece right here at the beginning, this work that I just did right here, this is telling me what the tail in terms of the series is going to. So the tail end terms are 1. So whatever these numbers are in the front, when I get to the end, I'm going to be adding 1, adding 1, adding 1, adding 1. And if I keep adding 1, I'm going to head to infinity. All right, so let's take a look at B. So for this one here, so what am I going to do? I know it's not geometric because n is not in the exponent. So then I'm going to do the only other test I know right now, and I'm going to take the limit to infinity. And then I'm going to put an implied 1 here, and then I have an equal rate of growth of n factorial. So then I just have to look at the coefficients. So that would be 1/2. So is 1/2 0? That is not 0. So then what is my conclusion here? That the sum of the series diverges. Okay, and then again, just to make sure we get this, so when I substitute in 1, I'm going to get a value. When I put in 2, I'll get a different value. When I put in 3, I'll get a different value. And when I'm close to infinity, whatever that means, what are going to be those tail end numbers? Those tail end numbers are going to be 1/2, because that's what this is telling me. This is telling me, what does the sequence converge to? The sequence converges to 1/2. Meaning the end numbers are going to be 1/2, right? So it's approaching 1/2 at the tail end terms. So whatever this adds up to, what am I going to keep adding at the end? When I head to infinity, I'm going to keep adding 1/2. And if I keep adding 1/2, what's going to happen? Those numbers are going to go to infinity, which means the sum of that series is going to diverge. And that's it.